Dr. Matt. In this series of videos, we're trying to explain some of the mysteries of quantum physics and relativity, such as wave-particle duality of light, superposition of states. The Schrodinger's cat is both dead and alive. It's crazy. Why mass curves spacetime, and other intriguing stuff like that. Well, in the first 7 videos, we tried to show that with almost no math. So, of course, we couldn't go into, the very tiny details, but at least we were able to explain things just by, defining very precisely some of the basic concepts in physics. And then you just use logical reasoning. In the second part, we'll use some math tools and try to explain why we use those tools and to resolve those mysteries, and explain the basic concepts in quantum physics and relativity. Of course, we won't go into the complicated, details because they're really complicated. Okay, but this will be enough to understand, all those basic concepts in quantum physics and relativity, and also resolve those mysteries that we were talking about before. So much fun. Okay, so let's go. So, in this particular video, we're going to see the main characteristics of complex numbers, and why they're so interesting to model some of the physical world characteristics themselves, the isomorphism between physical world and mathematical world. There will be another couple of videos about complex numbers, one of them that will give examples on how we can use them, in particular in quantum mechanics. And the other one will be to explain, the mysteries that we saw in quantum physics. That's fascinating. So, as said before, in this presentation, we're going to see some generic properties of complex numbers and why they're interesting as math tools in general. Complex numbers are extension of classical numbers, the real numbers that we use in our classical 3D space, for instance. Unfortunately, there's not much intuition, in using complex numbers in quantum physics or in relativity. It's just that they are convenient and flexible tools to mimic the behavior of quantum particles, as we will see in a moment. In other words, they are math objects which are isomorphic to some characteristics in our physical world. Remember? And that's what we want, to be able to explain some of the mysteries in quantum physics. So that's why in quantum mechanics or theory of relativity, vector spaces are defined over the field C of complex numbers, not the real number. And we'll see why in specific examples in one of the next videos. Now, one of the main reasons is that complex numbers can be defined in many different ways. Actually, it's their strengths, So let's see that in more details. Okay, so this is a classic definition of complex numbers, which I'm sure you're already aware of. Now, there are other ways to define complex numbers, and here, when I say equivalent definitions, I mean, with similar operations to addition and multiplication that can be applied to isomorphic sets of elements. So, for instance, a couple of real numbers, a couple of ordered real numbers can be viewed as a complex number. Or similarly, of course, a 2D vector over R. Now, they can be also viewed as coordinates of a point, in a geometric plane, like here, for instance. Here, you can see this P point here. And it has, from the origin, you can draw a vector like this, and you can see the coordinates, A here and B there. And that also allows to introduce the support for trigonometric functions, like sine, cosine. So here, for instance, for the same vector that we just saw, well, there is this segment here, which is equal to A cos theta, and this one here, which is A sine theta. And from there, you can also introduce the notion of complex exponential, which is cosine omega t plus I times sine omega t. Why use complex exponentials? Well, because they're easier to multiply and of course exponentiate, but also because they're easier to derive and or integrate. Because the derivative of exponential is an exponential. And finally, in this list, you can also represent them as matrices, like that. So why use complex numbers in quantum physics? Well, many aspects of quantum physics cannot be explained very intuitively, and there are mathematical reasons why complex numbers will work better than real numbers. Here, I give some examples, of those aspects. But there are mathematical reasons why complex numbers work better than real numbers, like algebraic closure or diagonalization of Hermitian operators and other peculiarities that we'll see in the next videos. But again, their main strength is that they can represent many different forms of math objects and therefore, our physical world objects. So basically, they work better because, they seem to mimic some of the quantum particle behaviors, and because they can take many different forms, they will help to simplify this modeling. Of course, you don't have to use complex numbers, but they really simplify things. And again, because they can be considered as points in a plane, but also can represent periodic functions, or because some operations are not symmetric, like in physical world, when you measure quantum particles, the order you use to measure some properties, can vary depending on the order of the measurements. And there are more complex mathematical reasons that we will see in more detail in the coming videos. So stay tuned.